Hello again, and now we're gonna do a quick summary of Chapter 5, Probability in Civil Engineering. So how do we use it? What are the rules? What are the formulas, right? And it's a very powerful tool because it helps us predict many things like bridge failure rates, traffic flow, stormwater runoff, uncertainty in most things. And uncertainty is all around us, right? No one can say they know something absolutely for sure is in civil engineering because we have a lot of factors interacting at multiple points in time, right? So probability gives us a structured way to really think about it. And we need to understand initially when we want to talk about probabilities is what is deterministic and what is stochastic in system analysis. Deterministic systems and events behave predictably. They're always the same. They're always in the same fashion, repeating themselves. So if you know the inputs, you should know the output. Like x equals 1, it will always be equals 1. 1 plus 1 is always equal to 2. That idea is deterministic. It is like calculating the load on a beam using Newton's law, for example. Like when we put a point load at the center of a beam, then it has a certain function, a certain formula, and we will always have the same answer. It's always predictable. This is the load, then this means this is the moment, this is the shear, and so on and so forth. Stochastic systems, on the other hand, involve uncertainty. So think about how traffic varies at different times of the day. For example, if you drive at 3 a.m. in the morning, the road is empty. Come at 7 or 8 or 9 when there is rush hour or when people leave work, and maybe you take 3 to 4 times the usual time to get back home, right? So civil engineering is increasingly reliant on stochastic modeling because we deal with a lot of factors interacting. Although some of them have a deterministic nature, like compressive strength, yield, and all these factors of the components and the materials that we use, the real world data is messy, like interacting the whole time, all of them together. And therefore, systems rarely behave, as expected. So before diving into the formulas, let's understand the fundamental set operations, the fundamental use of set operations. So suppose that you want to know the probability of either event A or event B occurring. This is presented as PAUB, which is a union, right? At first glance, one might think that it is the probability of A plus B. But if we do that, then we are counting something in the middle twice, which is called the intersection, right? So in order for us to actually calculate the union correctly, we need to subtract the intersection once. This leads us to the formula that we have learned in class for handling compound events, because simple events are different. So this is for handling compound events, which is PAUB is PA plus PB minus PA intersection B once, right? And therefore, going forward, the study becomes the study of what type of intersection do we have. And also understanding the question, of course. When we say at least one or either A or B, it means we're talking about union. When we say A and B, then we're talking about the intersection. So we need to really understand and read the question carefully, right? So simple events involve only one condition, like a beam failing under test, flipping one coin, and so on. Compound events involve multiple things happening together, like a beam fails and the soil settles, or flipping 2 coins or 2 dice, right? They will both give 2 different results or the same result, but they will contribute to the final product together. Mutually exclusive events cannot both happen at the same time. They cannot coexist. They cannot be together in the same room, right? Like if you rolled only one die, you rolled 1, you cannot get 3 and 5. It's either 3 or 5. It only has one output. It is impossible for it to have two outputs, right? It is illogical for a die to have two outputs. Non-disjoint or sequential events could both happen together, but they're not necessarily related. They can be related or unrelated, but both can happen at the same time. Therefore, we have two types of sequential events or non-disjoint events: statistically independent events, which have no relationship between each other, they do not affect each other, or statistically dependent events, like, for example, a corrosion accelerating cracks. When we have corrosion in beams, it starts expanding, creating cracks in concrete. There is a direct relationship. They affect each other. So one leads to the other. This leads us to a bunch of formulas. So mutually exclusive events, it's PAUB equals PA plus PB. Why? Because minus PA intersection B is 0. They're mutually exclusive. They cannot coexist. So their intersection is a 0, right? Non-disjoint events, it's PA union B, which is equal to PA plus PB minus PA intersects with B, a normal intersection. And now we look at the derivatives of that, independent and dependent. So if it is statistically independent, the intersection is PA times PB. If it is dependent, PA intersect B is PA times PB given A. The one we put at the beginning becomes the denominator in the second part of the multiplier. So understanding your problem, understanding what you are dealing with, helps you arrive at the right understanding and the right formula logic. Now let's go even deeper, from raw probabilities to distributions, because once we calculate enough probabilities, we can convert them into distributions, right? And these distributions evolve into something called expected values, which is the final valuable outcome or expected outcome of this interaction. So a probability function maps outcomes to their likelihoods. This could be discrete, like failure counts, or continuous, like time of failure, right? Like a full function that continues. And then there is the expected value, which is the long-run average result if the experiment is repeated many times, is repeated in the most likely value, It is calculated two ways, either sigma x times px for discrete variables. So the probability of a value x, the probability of an event x times the general value. For example, the probability of you having a fine, is 30%. The value of the fine is, let's say, $200, right? So the expected value is the probability, which is 0.3 times the value, the general value, which is 200. So 0.3 times 200 is 60. So the expected value is 60. For continuous ones, the ones with functions, it is sigma integral x of x. Which is also a form of sigma, right? Integration is a form of sigma. It's the summation of these little points, little areas under the curve, so that you will get the full area under the curve. So sigma x of x dx for continuous ones. This is especially useful in cost risk analysis and replacement scheduling. Now, these concepts exist a lot in civil engineering, from assessing if a condition is good or average or excellent, to how many structural units will have defects, impurities, or both in a supply batch. What is the likelihood a civil system with 3 components fails if any one fails? So these problems involve everything from mutually exclusive events to dependent and compound probabilities. And you should practice solving them. We have lots of examples in the slides, lots of examples in the book. So you need to really formalize yourself with these types of problems and be comfortable with them. They're all very easy and straightforward. So when should I use probability? Well, generally, whenever you're dealing with something uncertain, like when something is not 100% sure, 100% clear. So failure prediction, safety assessments, environmental modeling, anything that requires you to design under uncertainty. So to gain some confidence, we add probabilistic math to the equation to become more sure, more certain of what is the path forward. It is not just about calculating odds, it's about making informed engineering decisions when stakes are high and the data isn't quite perfect. So, in summary, engineering systems often involve uncertainty. Probability helps quantify and manage risks. Different event types require different rules, especially in the real world. And real world decisions, from bridge replacements to evacuation planning, depend on probabilistic thinking and your understanding of probabilities, your proper understanding of probabilities. Going forward, we will merge this with statistics as well to see how we can make better decisions based on bigger sizes of data. Hope this helps and best of luck.